Welcome to this lesson on AP Statistics. Today we are focusing on topic 3.15, carrying out a chi-square test for homogeneity or independence. By the end of this video, you will be able to perform a complete chi-square test from start to finish. We will go through the mechanics of the formulas and then walk through two full-length examples to see how this works in practice. Before we dive into the math, we need to understand the data structure we are working with. In these tests, we use two-way tables, also known as contingency tables. The layout is simple. Rows represent variable A, columns represent variable B, and the cells contain observed counts. Whether we are testing for homogeneity or independence, the table looks the same. The difference lies in how the data was collected. For independence, we take one sample and measure two variables for each individual. For homogeneity, we take two or more samples and measure one variable for each. For example, if we ask one group of students their favorite subject and their gender, that is a test for independence. If we take separate samples of seniors and freshmen and ask them if they like school lunch, that is a test for homogeneity. The calculation process, however, is identical for both. The first step in any chi-square test is determining what we expect to see if there were no relationship between our variables. This is called the expected count. Our goal is to calculate expected counts for a two-way table. Under the null hypothesis, we assume the distribution of the categorical variable is the same across all groups. To find the expected count for any specific cell, we use the row and column totals. Let's look at this small table. To find the expected count for men who said yes, we look at the row total for men, which is 50, and the column total for yes, which is 60. The calculation is 50 times 60 divided by 100. Multiplying 50 by 60 gives us 3,000. Dividing by the table total of 100 gives us an expected count of 30. Notice that while the observed count was 20, the expected count is 30. This difference is what our test will eventually measure. We repeat this for every single cell in the table. Once we have our expected counts, we can calculate how much our observed data deviates from what we expected. This is the chi-square test statistic. The formula for the chi-square statistic looks like this. Chi squared equals the sum of the quantity observed minus expected squared, all divided by expected. We calculate this specific value for every cell in our table and add them all together. Squaring the difference ensures that positive and negative deviations don't cancel each other out, and dividing by the expected value scales the difference relative to the size of the group. To use this statistic, we also need to know the shape of the chi-square distribution we are using. This is determined by the degrees of freedom. Degrees of freedom formula: df equals the quantity number of rows minus 1 times the quantity number of columns minus 1. For our previous 2 by 2 table, that would be 2 minus 1 times 2 minus 1, which equals 1 degree of freedom. If we had a table with 3 rows and 4 columns, the degrees of freedom would be 2 times 3, which equals 6. After calculating our test statistic, we need to find the p-value to make a decision. The p-value is the probability of getting a chi-square statistic as large as, or larger than, the one we calculated, assuming the null hypothesis is true. Chi-square tests are almost always right-tailed because the square differences are always positive. A larger chi-square value means a larger difference between what we saw and what we expected, which results in a smaller p-value. To actually get the number, we use technology or a chi-square probability table with our degrees of freedom. In AP Stats, you'll often use a calculator's chi-square CDF function or a specialized test menu. Once we have that p-value, we compare it to our significance level, alpha, which is usually 0.05. If the p-value is less than alpha, reject the null hypothesis. If the p-value is greater than alpha, fail to reject the null hypothesis. Rejecting the null means we have convincing evidence of an association or a difference in distributions. Failing to reject means we do not have enough evidence to say a relationship exists. Now that we have the theory down, let's apply it to a full-scale problem. We will start with a test for independence. Consider a researcher who wants to know if there is an association between the type of music a student listens to and their academic performance, or GPA. The sample consists of 200 randomly selected college students. In a test for independence, we are looking at one population and asking two questions. Here, the population is college students, and the two variables are music preference and GPA level. Let's look at the data table of observed counts. Take a look at the observed counts. Before we calculate anything, notice that it looks like classical listeners might have more high GPA counts relative to their group size, compared to pop listeners. But is this difference statistically significant, or just due to random sampling variability? Our first task is to state the hypotheses. The null hypothesis, H0, is that there is no association between music preference and GPA level in the population of college students. The alternative hypothesis, H-alpha, is that there is an association between music preference and GPA level in the population of college students. Notice that for independence, we use the word association or independent. We are making a claim about the entire population based on this sample. Before we calculate the test statistic for our music and GPA example, we must check the conditions to ensure our inference is valid. First, the random condition. Data must come from a random sample or randomized experiment. Second, the 10% rule. If sampling without replacement, N must be less than 10% of the population. Third, large counts. All expected counts must be at least 5. First, the problem states that 200 students were randomly selected. This satisfies the random condition. Second, it is safe to assume there are more than 2,000 college students, so the 10% rule is met. Third, we need to check the large counts condition. This requires us to calculate the expected counts for all 9 cells in our table. The expected counts under the null hypothesis can be calculated using the formula row total times column total divided by the table total. Let's calculate a few together. For classical music and low GPA, we take the row total 60 times the column total 60 divided by 200, which equals 18. For classical music and mid GPA, we take 60 times 95 divided by 200, giving us 28.5. And for rock music and high GPA, we take the row total 80 times the column total, 45 divided by 200, which equals 18. Here is the full table of expected counts for our dataset. Looking at the table, the smallest expected count is 13.5. Since every value is greater than or equal to 5, the large counts condition is met. We are clear to proceed with the chi-square test. Now let's calculate the chi-square test statistic for our music and GPA data. We need to take each observed value, subtract its corresponding expected value, square that difference, and divide by the expected value. For cell 1, we have 10 minus 18 squared divided by 18, which is 3.556. Cell 2 gives us 30 minus 28.5 squared divided by 28.5, equaling 0.079. Cell 3 is 20 minus 13.5 squared divided by 13.5, which is 3.130. Cell 4 results in 0.042. Cell 5 gives 0.105. And cell 6 results in 0.500. Finally, cell 7 is 2.72, cell 8 is 0.430, and cell 9 is 0.907. Summing all these components up, 3.556 plus 0.079 plus 3.130 plus 0.042 plus 0.105 plus 0.500 plus 2.722 plus 0.430 plus 0.90. 7 equals 11.471. Our chi-square test statistic is approximately 11.47. Next, we need the degrees of freedom. Since our table has 3 rows, classical, rock, and pop, and 3 columns, low, mid, and high GPA, the degrees of freedom is 3 minus 1 times 3 minus 1, which is 2 times 2 equaling 4. With a chi-square value of 11.47 and 4 degrees of freedom, we can find our p-value. Using a calculator or a chi-square table, we find the area to the right of 11.47. The p-value, the probability that chi-square is greater than 11.47 with 4 degrees of freedom, is approximately 0.0218. This p-value of about 0.022 tells us that if there truly was no association between music and GPA, we would see a result this extreme only about 2.2% of the time, just by chance. Now we reach the final step, making a conclusion based on our p-value. Since 0.0218 is less than our significance level of 0.05, we reject the null hypothesis. Because the p-value is less than alpha, we reject H0. There is convincing evidence that there is an association between music preference and GPA level for the population of college students. In AP statistics, your conclusion must always include 3 things. 1. An explicit comparison of the p-value to alpha. 2. A decision to reject or fail to reject the null. 3. A conclusion in context of the alternative hypothesis using non-definitive language like evidence of an association, rather than proving an association. We should also look back at the individual components of our chi-square calculation to see what drove this result. Notice that the classical row had the largest differences. There were fewer low GPA students and more high GPA students than we expected. This suggests that the association we found is likely driven by the classical music group performing differently than the others. Now let's switch gears and look at a test for homogeneity. While the math is the same, the context is different. We use this test when we have multiple populations or groups, and we want to see if the distribution of a single categorical variable is the same across those groups. Let's look at an example involving regional chip flavor preferences. A snack company wants to know if the preference for potato chip flavors is the same in 3 different regions of the country: Northeast, South, and West. Independent random samples were taken from each region. Here is the data table showing the counts for barbecue, plain, and sour cream flavors across the 3 regions. In this case, the groups are the regions, and the variable is the flavor preference. We aren't testing for an association between 2 variables within one person. We are testing if the distribution of flavor preference is homogeneous, meaning the same across the 3 regions. Our null hypothesis, H sub naught, states that the distribution of potato chip flavor preferences is the same across the Northeast, South, and West regions. And the alternative hypothesis, H sub alpha, states that the distribution of potato chip flavor preferences is different for at least one of the 3 regions. Take a moment to look at the phrasing. For homogeneity, we focus on whether the distributions are the same or different. Let's quickly verify our conditions for this regional flavor study before moving to the calculations. First, the random condition. The problem states independent random samples were taken from each of the 3 regions. Second, the 10% rule. It is reasonable to assume there are more than 1,200 people in each region. And third, large counts. All expected counts must be at least 5. To check the large counts, we need the expected values. Notice that all region totals are the same at 120. This will make our calculations a bit more repetitive but easier to check. The formula for an expected count is the row total times the column total, all divided by the table total. For barbecue in any region, we take 120 times 130, divided by 360, giving 43.33. For plain, it is 120 times 120 divided by 360, which equals 40. And for sour cream, 120 times 110 divided by 360 gives 36.67. Here is the full expected counts table. Notice how the values are identical across rows because our sample sizes for each region were the same. Since all expected counts are well above 5, the large counts condition is met. We can proceed with the test. Note how the expected counts represent what the table would look like if every region had the exact same taste in chips, adjusted for the sample size. Now, let's compute our chi-square statistic for the regional chip preferences. We will take each observed count, subtract the expected count of 43.3, 40, or 36.7, square it, and divide. First, for the Northeast region, we calculate the components for barbecue, plain, and sour cream flavors. Next, for the South, we see larger deviations in the barbecue preference, contributing over 6 to our sum. And finally, for the West, the sour cream preference also shows a notable difference from the expected count. Summing all 9 of these values gives us our final test statistic. Our total chi-square test statistic is approximately 23.05. Next, we calculate the degrees of freedom. Like the previous example, we have 3 rows and 3 columns. Using a chi-square distribution with 4 degrees of freedom, we look for the area to the right of 23.05. The p-value, which is the probability of chi-square being greater than 23.05, is approximately 0.0001. This p-value is extremely small. It means that if the flavor preferences were actually the same across all regions, the chance of seeing a sample difference this large is about 1 in 10,000. With a p-value of 0.0001, we are ready to make our final conclusion. Because the p-value is less than 0.05, we reject the null hypothesis. There is very strong evidence that the distribution of potato chip flavor preferences is different for at least one of the 3 regions. Just as before, we should perform a follow-up analysis to see which groups deviated the most. The largest contributors to the chi-square statistic are South barbecue at 6.413, West sour cream at 4.846, and West barbecue at 4.104. The data shows that people in the South preferred barbecue much more than expected, while those in the West preferred it much less. The West also showed a much higher preference for sour cream than expected. In a real-world scenario, the snack company could use this information to adjust their shipping and marketing strategies. This is the power of the chi-square test. It doesn't just tell you that things are different. The individual components help you see exactly how they are different. By comparing the observed and expected counts, you can tell a much richer story about your data than just rejecting the null. To wrap up, let's compare the two types of tests we just performed. While the math is identical, the distinction is important for your AP exam. The test for independence typically involves one population where we measure two variables to see if there is an association. On the other hand, the test for homogeneity compares two or more populations on one variable to see if the distributions are the same. In the music example, we sampled college students as one big group and looked for an association. In the chip example, we purposefully sampled 3 different regions to compare them. Here are the key formulas to remember. First, the expected count is the row total times the column total, divided by the table total. Second, the chi-squared statistic is the sum of observed minus expected squared, divided by expected. And finally, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Always remember to check your conditions, random, 10%, and large counts, before doing the math. If all expected counts aren't at least 5, the chi-square distribution might not be a good fit for your data. A final tip: use non-definitive language in your conclusion. Say, there is evidence to suggest, rather than, this proves. You are now equipped to handle chi-square tests for two-way tables. Practice calculating a few expected counts by hand, and then try running the full test on your calculator to get comfortable with the technology. Good luck with your statistics journey.